All right, so we'll get started here. I hope you all had a good weekend. Happy Monday, everybody. We are continuing on here. We got your quizzes. We'll get them graded this week. Your grades should be posted by Thursday or Friday of this week. And then your first lab is due tomorrow, so make sure you wrap that up and submit that tomorrow in CCLE. Okay, so today we are going to take a look at Chapter 4. Chapter 4 is all about describing associations and relationships between numeric variables. Okay, and we're going to take a look at a couple concepts. There's correlation and there's linear regression. Okay, so those are kind of the key ideas here. Sorry, let me just here. Okay, all right. So I want to talk a little bit about the big picture first, okay? And that is that in statistics, what we're trying to do is we're trying to make conclusions from data. And so before we can get even into starting to make conclusions from the data, we have to be able to describe the data. And that's what we did last week. We looked at chapters 2 and 3, and those were all about describing data. We looked at one variable at a time. And in chapter 2, what we did was we described data with pictures. So we saw histograms, we saw dot plots, and bar charts. And in chapter 3, we described data with numeric summaries. So we had things like the mean and the median, and things to describe the amount of spread, like the standard deviation and variance and IQR and things like that. Okay. And in today's chapter, we are still continuing describing data. Okay. Except this time, what we're going to do is we're going to describe the relationship between two variables. Okay. And in particular, we're going to be describing the relationship between two numeric variables. So, so we'll look at, say, we'll look at two numeric variables, and we want to be able to describe the relationship between them. Okay. So when we talk about describing relationships between variables, we have to keep in mind that oftentimes we're looking at, for one observation, so for one, let's say we're measuring things about a person, or measuring things about a house, whatever it might be, we might record multiple variables for each observation, okay? So for a person, you might record that person's height, and that person's weight, and that person's age, okay? And we can ask, is there a relationship between height and weight? Is there a relationship between height and age? Is there a relationship between weight and age? Things like that. And so for like children, there's probably going to be a very strong relationship between age and height. You know, as kids get older, they usually get taller and things like that. Okay. Another example here that I've put on my slide is, maybe we're going to look at houses in the neighborhood. And what we can do is when we look at houses in the neighborhood, we might record or write down the size of the house, like how many square footage is the house, and the estimated value of the house, all right? And in general, when you do something like that, you'll see a trend where houses that have a higher value, houses with more square feet will have higher value. Houses with fewer square feet, like a smaller house, will have lower value. That's going to be the general trend, especially if you're looking within one neighborhood, okay? And then, so we would say there's a relationship between the size and price of a house. So keep in mind, these are within the same house, we're measuring multiple things about the house. In this case, the size of the house and its value, right? And what we will do today is, rather than just saying, bigger houses generally cost more, smaller houses generally cost less, which is a perfectly valid way of describing the relationship, we're going to quantify it. Okay, we're going to say each additional square foot is associated with an increase of $350 to the value of the house, or something like that. Okay, so we're going to quantify that relationship. Okay, and that's what we're going to cover today. So so a lot of this is going from just general concepts and ideas which are very quick and easy to explain and pick up, to quantifying it with numbers so we can be specific in our descriptions, right? So we can say, when we're talking about spread, we can say in the second grade classroom, when you look at the students' ages, there's very little spread. And if you go to the DMV waiting room and you look at the ages of pupils in the DMV waiting room, there's lots of spread, okay? And rather than just saying little to lots of spread, we learned last week how to quantify that. We can say the standard deviation is 0.3 and the standard deviation is 17.4, okay? And again, today, rather than just saying bigger houses cost more, smaller houses cost less, we're going to quantify it and say, if you have another house that's 1 square foot bigger, you can expect it to cost $350 more, something like that. Okay, that's kind of the idea that we're going for today. All right, so here I'm going to just kind of a simple example is we are going to look at some census data. Okay, so you see, you can get a lot of good data gathered by our government. Every 10 years, the U.S. conducts a census, and here's some information on kind of marriage information, and this is looking at the age of first marriage over time. Okay, and so they just during the census they interviewed some people, and they say are you male or female, and how old were you when you first got married? Okay, and this is what it looks like, and so the first most recent information is in the year 2019, the average age for men in their first marriage is 29.8, and the average age for women in their first marriage is 28.0. These are not this is just the average of kind of all men and the average of all women, and it's not necessarily that they're married to each other or anything like that. Okay, and obviously this it's an average, it's a mean. So there are people whose first marriage is older, and there's people whose first marriage they are younger. Okay, and this is kind of what we see here. In 1940, when they asked, how old were you when you first got married, the average age for men was something around 24.3. The average age for women was something around 21.5. Okay, and this got a little bit cut off, but I think the very first measurement was in 1890, and it was 26.1 and 22.0. Okay. All right, and so here we can plot, and so each observation here, keep in mind, is not an individual person or anything like that. It's the year. Okay, and so each dot on the next plot represents a different year, and we don't know which year it is, but whenever this survey, whatever year this represents, who knows, maybe the year 2010, I don't know. The average age of first marriage for men was around 28. Average age of first marriage for women was around 26, and things like that. And what we see is that there's an overall very strong trend in that what we can say is that in the years where the average age of marriage for the men was high, the average age of marriage for the women was also fairly high, okay? And in years where the average age of marriage for the men was pretty low, the average age of marriage for women was also pretty low, okay? This is kind of what we're seeing. So there were, several years where the average age of marriage, of first marriage for men was around 22, okay? And average age of first marriage for women was around 20, okay? And that's, I imagine quite a few of you are around 22, 20 years old, and this was the average, which meant some people, okay, again, an average means some people got married earlier and some people got married later, and this is kind of the average there. So, definitely things have changed. So anyway, this is, and when the data was first being collected, the United States only had, male-female marriages, and in recent times that has changed, and but you can still ask, what's kind of, when was your first marriage, okay? And right now the only men and women are represented, but perhaps in the future they would include a non-binary average as well. So, but okay, so this is just some comments that I've written here, is that there's a very strong relationship between the men's average age of first marriage and a woman's average age of first marriage. In years where the average age of men's first marriage is high, the women's average age of first marriage is also high. And in years where the average age of men's first marriage is low, the woman's average age of first marriage is also low, okay? And if you look at the data, there's consistently about approximately a 2-year difference between the average ages, okay? And there are a few exceptions over here, but overall there's a pretty strong relationship that says, about a 2-year difference, okay? If you can also create another scatter plot using the same data, and this time I'm plotting the year versus average age of men's first marriage and average age of women's first marriage. And this reveals an interesting trend, is that in the 1890, 1900, men's average age of first marriage was around 26, and consistently that seems to go down and down and down until around the 1960s, when the men's average age of first marriage looks to be around 22 years of age. And then after 1960, consistently year over year, the average age of first marriage seems to get later and later and later. So, in the year 2000, something around 27. In the year 2020, something around closer to 30, okay? Something similar happens also for women's average age of first marriage, where in 1890 it was around 22, seems to go fairly downwards until around the 1960s, and then consistently year after year, getting higher and higher until around 2020, when the average age of first marriage is around 28, okay? Just some interesting trends there, okay? And in these cases, we would not be able to say there's a linear relationship, okay? Because there's one single straight line cannot describe the overall trend. Perhaps 2 straight lines, okay? A line from 1890 to around 1960, and then the line from 1960 to around 2020. Okay, similar here to here. And what's interesting is that the slope of kind of over on this side is a little bit steeper, whereas over here for women it's not as steep, and there's some interesting trends there as well. So just something interesting to kind of note. So oops. All right, so what we might say is that, there is a very strong relationship between the year and average age of first marriage for both men and women, okay? But what we can't say is the relationship cannot be defined with a single straight line, okay? So it appears from around 1890 to around 1960, continues to decrease, okay? And then from around 1960 to 2020, it continues to increase, okay? From around 22 to 30 for the men and around 20 to 28 for the women, okay? All right, and so that's just kind of, you know, we're looking at scatter plots where we just kind of plot each of the data points as a dot in the graph here, but what we'll do is we'll kind of formalize how we should go about describing a relationship. Okay, and so when we describe a relationship, there's a few things that we want to point out and you know, be sure to mention, and those are things like the shape, the trend and the direction, the strength, and if there are any outliers. All right, and so regarding shape, the shape of a relationship, we're going to say the relationship can either be linear or nonlinear. Okay, and I've just taken examples out of our textbook. Okay, and linear just means that when you create a scatter plot, the overall relationship can be summarized with a single straight line. Okay, whereas nonlinear means that the relationship should not be summarized with a single straight line. So here, the overall trend with the dots looks like a straight line does the trick, okay? And apparently, I guess looking at over the course of time, I think they looked at like online searches, and there seems to be kind of a trend where when people search for vampires, frequently they're coincides with searching for zombies frequently, and times where people are not searching for vampires very often. They are not searching for zombies very often either. I'm not sure what we're trying to say here, but that's the relationship there, and it seems to be able to be described with a single straight line. Okay, over here we have a nonlinear relationship where we should draw kind of a curve to describe the overall trend and the dots here. And this is a relationship between temperature and ozone parts per million and things like that. And there's a non-linear trend or relationship where we would not want to use a single straight line. Okay. As far as direction goes, the direction of a relationship can be positive, negative, or neither positive nor negative. Okay. And so a positive relationship means that large values of x are associated with large values of y, and small values of x are associated with small values of y. Okay, and then in a negative relationship, it's just kind of the flip of that. Large x goes with small y, small x goes with large y. And then if it's neither positive nor negative, then large values of x are not associated with either large or small values, or maybe associated with both. And similarly, we can't say anything about the small values of x, which may or may not be associated with large or small values of y. So I think, you know, this is a little bit all abstract. Maybe some examples will be better for this, okay? So here is a positive trend, okay? And the two variables here will be the age of the car in years and the number of miles driven on that car, okay? And so large X, a positive relationship means large X goes with large Y. So if you look at large X, that means you have an older car. And in general, older cars will have more mileage on them, okay? Higher miles driven, okay? And newer cars where age is low, where X is low, the Y value will also be low. We expect for newer cars, the number of miles driven to be quite low, okay? There's some exceptions. Here is a car that's maybe only 6 years old and yet has 240,000 miles on it, which is we would consider to be an outlier, okay? And then here's a fairly old car, maybe 22 years old, and has only maybe 60,000 miles on it or something, 70,000 miles, which is quite low comparatively, okay? But the overall trend is that as the car gets older, we see more and more miles driven on it, okay? here is the a negative trend, okay? A negative trend means that large X goes with small y and small x goes with large y. And so this shows, I think, each dot here represents a different country, okay? Each dot represents a different country, and within that country, and I think this is also measured over time, so at different points in time, so that what we see here is that here is a country with a fairly low literacy rate, okay? So I don't know, some country, perhaps maybe a few decades ago, the literacy rate is less than 20%, and there appears to be a there's a negative trend. And so this country with low literacy also has total births per woman, okay? So this is, kind of it's just a general metric of fertility is not really the correct word, but just general metric of how many births there are per woman in the country, right? And this is not saying that. So this is saying on average the total births per woman is something around 7.5. So that means some women had more than 7.5 children. Some women had less. Some might have none, but then when you kind of average and take the total number, it's something around there, okay? And what we see is that, as the literacy rate increases, the total births per woman, the general trend is that it decreases, okay? So in countries where there's around 100% literacy rate, total births per woman is somewhere around 2, maybe a little bit lower, 1.5, maybe up to around 3, but in general, lower, okay? Now there's quite a bit of spread, okay? So, these two countries, this dot down here and this dot up here, they both have around a literacy rate of around 70%, and there's quite a big difference with this one having an average of around 2 and this one having an average around 7, okay? So there's certainly quite a bit of discrepancy, okay, quite a bit of spread, but overall the trend is that as literacy rate goes up, the total births per woman tends to go down. Now, we have to be careful and not make a cause and effect conclusion, okay? It's not, okay, the literacy rate, okay, may or may not have a direct effect on the number of births per woman. It's not that saying that as soon as we get people to read and educate them, that causes them to have fewer children, okay? There are different confounding variables that could be at play here, okay? So there could be, historically, it was, historically, families would often choose to have many children when there was high infant mortality. So when, if children did not have a high survival rate, a lot of children died before the age of 5. In those places, and again, this could be a few decades ago, many families chose to have many children because, or I guess, chose to have, many births. Okay, in that, there's high infant mortality, and so, and that might have been associated with a time of low literacy, and so it may not necessarily be that literacy is the thing that's causing the total births per woman, or the total births per woman is causing a higher or lower literacy rate. But there's other factors at play, right? Like just the kind of access, the infrastructure and access to healthcare and access to education of a country that is developing could lead to changes in both of these variables. All right. And so, so we have to be careful not to make cause and effect conclusions when we see some kind of trend like this, okay? All right, so there might, sometimes we're tempted to jump and say, okay, what we need to do is we need to increase access to education. Okay, absolutely, access to education is definitely something that that is good, but that in of itself may not necessarily cause these changes. Okay, it could, but we don't know. There's a lot of other things at play. All right, and here's an example of a trend that is neither positive nor negative, okay? And so here is, we looked at the times, race times of Forest City Marathon. I don't know what marathon this is, okay? It's not like a highly competitive one, okay, it appears. And we looked at the age of the runner and how long it took them to complete the marathon. And so we have, a lot of people around 20 years old who finished the race quickly or took a lot of time. We have people who are around 40 years old who finished the race quickly or took a lot of time. People, older people in the race who, 65, 70, took little or high amount of time. And so we can neither say that high age is associated with fast or slow times or low age is associated with fast or slow times. There is neither a positive nor a negative trend here. All right, here's another example of neither positive nor negative trend. Okay, this is just some simulated data. Now, on this previous one, we would say there's no overall association between these two variables. Okay, there's no overall association. We can't really say that higher or lower ages are associated with higher or lower times, okay? Here, there is definitely an association between the two variables, okay? It's just that that association would have to be summarized with a curved line, okay? So there's definitely an association between the variables, but that association is going to be curved. And overall, that relationship, that association is not linear, and the overall relationship is neither positive nor negative, okay? If you look, if you split the data in half at x equals 0, like you draw kind of a vertical line, you cut it down the middle, the values on the left have a negative trend, and then the values to the right of 0 have an overall positive trend, okay? Positive nonlinear, this would be negative nonlinear trend. And so the overall data set has neither a positive nor a negative trend, okay? All right. How are we doing with all of this? Okay. All right, let me give you your first quiz answer. First quiz answer today for week 2 Monday is E. E as in elephant. First quiz answer for today is E as in elephant. So jot that down for your viewing quiz later. Okay, question 1, E as in elephant. All right, and then, okay, so as we continue talking about how to describe a relationship, what we want to mention now is the strength of a relationship, okay? The strength of a relationship kind of summarizes how much scatter appears in the scatter plot, okay? And you can also think of it as how well you can predict one variable based on the other, right? So, vague words, we can use words like weak or strong to describe the strength of a relationship. Later today, we'll quantify that. But just overall, we'll look at, what's a weak relationship and what's a strong relationship when we're talking about describing the strength of a relationship, okay? So here, these are kind of both moderate relationships, but if you look at these, when we compare these two, we would say this one is weaker. There's more scatter on the plot to the left, and there's less scatter on the plot to the right. So this one has the stronger relationship, okay? And what we did is we looked at some people. Each dot represents a person, and we recorded their height and their weight, okay? And we also recorded their waist size and their weight, all right? And so the overall trend is positive in both cases, okay? And the overall trend, I would say, is linear in both cases, which means, you know, generally taller people are associated with higher weight, shorter people are associated with lower weight, okay? And over in this graph, people with larger waist sizes are associated with higher weight. People with smaller waist sizes are associated with lower weight. Okay. But we would say the relationship on the right is stronger. So if you knew somebody was 70 inches tall, okay, that person's weight can go anywhere from, you know, anywhere from around 120 to 260, okay, in our data, right? Whereas if you knew somebody had a waist size of, say, 30 inches, you know, there's kind of a much narrower window in terms of values that we see. So 30 goes anywhere from 120 to maybe 170, 180, something around there. So kind of the amount of spread that you have for a particular value is a lot smaller on the graph to the right than on the graph to the left, okay? So if you know the waist size, your prediction regarding the weight is likely to be more accurate than if you were trying to make a prediction based on height alone, okay? And so because there's less scatter, we would say this has a stronger relationship. There's more scatter over here. We'd say this is a weaker relationship between the two variables, okay? They're both positive, have positive relationships that are linear, though. Okay, and so here we can create that plot for the different years. Again, each dot here represents a different year, and we're looking at the average age of first marriage for men and the average age of first marriage for women. And there is a we would say it's linear, it's positive, and there's a very strong relationship in that, you know, if you knew the average age of marriage, first marriage for men, you can probably get a fairly good, pretty accurate prediction for the average age of first marriage for women, okay? Just because the if you drew a straight line and you said how much scatter is there around the line, there's not a whole lot of scatter around the straight line, okay? So does the strength of a relationship also apply to nonlinear plots? Yes, you can talk about you know, the strength of a relationship for a nonlinear plot. We won't be able to quantify it in our class, all right? So in our class, we're looking at the strength of a relationship only for linear relationships, and we're going to use correlation, or Pearson's correlation is what's known. If you do take another statistics course in the future, you might learn how to quantify the strength of a relationship for nonlinear relationships, and it can be used for that, but just but we don't get to cover that in our class here. All right, so this is what we have, okay? It's important that when we describe relationships that we use phrases like tends to or in general, because anytime we describe some kind of relationship, there's variability, right? The association that we describe is not going to necessarily be true for all individuals, right? So, so here we can say, you know, in years where there were the average age of women was high, or average age of men's first marriage was high, tended to be years where the average age of women's first marriage was also high, and things like that. But of course, you know, if you look at individual years, you know, in this year, the average age of men's first marriage is something around 25, and the average age of women's first marriage is something, you know, maybe around 22 and a half. Whereas over here, we have a dot where the average age of men's first marriage is around 26, but the average age of women's first marriage is lower at around 22. And so it's not going to necessarily apply for each individual point on the graph, but, you know, overall, when we're talking about a general trend, we can say, you know, this tends to happen, but of course, it's not necessarily the case for all individuals, right? And then we didn't really do this, but if there are individuals that, individual dots that stand out or appear to be unusual or outliers, not part of the general pattern, it's probably worth noting, right? So you can say, let's see. So for example, this car, you might want to say, you know, there are a few exceptions. A car that was approximately 6 years old with very high mileage. This doesn't appear to fit the general trend. And this one I would say also doesn't appear to fit the general trend. If you were to draw a straight line, it would probably go somewhere like this, from you know, from one corner down here to, you know, probably around this corner up here. And we would say this dot and this dot don't generally follow the general trend, and we may want to kind of point those out as well. All right, so in this section on correlation, we're going to take, you know, all of the stuff that we've covered regarding describing the trend in a relationship, and we're going to quantify it. Okay, and so the correlation coefficient. Here's a few key points here. Okay, it's a number. It's a number that measures the strength and direction of our linear relationship. Okay. And the key is that it applies only to a linear relationship, all right? And, technically, you can calculate, it's just the result of a formula, and you are able to just plug in data points from nonlinear relationships, okay? And you can plug data points from kind of any data set, and it will spit out a number, okay? It's just that that number is not going to be meaningful. Okay, the number is only meaningful when we're talking about a linear relationship. The symbol that we use for the correlation coefficient is R, kind of R for like a relationship. And the number R, that value, will always be between negative and positive 1. Okay, it's always going to be between -1 and +1. Okay, if R is far from 0, meaning R is close to -1 and R is close to +1, that indicates a strong linear association. And if R is close to 0, that indicates a weak linear association. Okay, I guess assuming the relationship is linear, right? All right. And the sign of R is the direction. So if R is positive, the direction of the relationship is positive. If R is negative, the direction of the relationship is negative. So here is a plot, okay? Here, the correlation coefficient is exactly positive 1.0, okay? This indicates a perfect positive relationship, okay? And these dots lie exactly on a straight line, okay? And if and this one is positive 1.0 because the relationship is positive, okay? If the dots went in the other direction, you would have a negative relationship, right? And this means if you knew one variable, you can predict the other variable perfectly. So this is somebody's height in inches and their height in centimeters. And so basically, if you knew somebody's height in inches, you can predict their height in centimeters perfectly. And this is what we have. All right, here's a few more pictures that I've taken from our textbook that kind of just show as there gets more and more scatter, the relationship gets weaker, and this is reflected in the magnitude of R. Okay, so here there's a bit of scatter. This is the relationship between someone's height and their weight in pounds, and there's more scatter, and we would say R is 0.72. Okay, here is there's even more scatter, and so the correlation goes down to around 0.48. Okay, overall there's still a positive trend in in general, large values of x go with large values of y, small values of x go with small values of y. But there's quite a bit of scatter, and so we have r equal to 0.48, okay? And here there's quite a bit of scatter. You know, if I did not see this number, r equal to 0.19, I would have a hard time guessing what the correlation is. And I wouldn't even be sure if I would identify this as a positive trend. But so, you know, when you have R's that are less than 0.2, even less than 0.3, that indicates a fairly weak relationship, okay? So as, you know, when R is going down, there's a lot more kind of scatter. And this is just asking, is there a relationship between someone's GPA and their math SAT score? And apparently that relationship is fairly weak, okay? And this, you know, this would probably apply to the general population. I imagine, you know, if you looked at UCLA admits, probably most students had very high GPAs and most students had very high math SAT scores. That's just the general, if you look at the admission stats, okay? But kind of in the larger circle, you know, is there a strong relationship between math SAT score and GPA? No, not necessarily, okay? All right, so in our course, we are not going to bother learning how to calculate the correlation by hand, okay? So I'm not going to show you the actual formula or anything like that. The general idea is you convert your x and y values into z-scores, okay? And then you kind of multiply these together and add them up and divide. In practice, no one does this, okay? No one calculates the correlation coefficient by hand, okay? We almost always use a computer or calculator, and if you want to do something like that in R, you would you basically just use the function core for correlation, and you plug in your vector of x values and your vector of y values, okay? So in our case, if we wanted to calculate the correlation between men's age of first marriage and women's age of first marriage, we look at this and we'd say, okay, it's positive, and there's a very strong relationship. And indeed, when you calculate the correlation, you get a correlation of 0.985, okay? So remember the correlation, the maximum correlation is 1.0, and so here we're getting a correlation of 0.985, which is very, very high, indicating a very strong relationship between men's age of first marriage and women's age of first marriage. So that's what we have here. All right. And so this is how you can go about doing something like that in R. All right, here are some important rules for correlation. I don't know, start this slide. This is an important slide. Okay, so if you swap the variables, it will not affect the correlation value. Okay, so if x and y have a correlation of 0.75 and you swap them, the correlation between y and x will have the same correlation of 0.75. Okay, so swapping variables, which one is your x and which one is your y, is not going to affect the correlation. All right. If you add a constant or you multiply everything by a positive constant, that too will not affect R. Okay, so if you add 10 to every single value, that's not going to affect the correlation. If you multiply every number by a positive value, okay, so you can't multiply it by a negative and you can't multiply it by 0, but if you multiply it by a positive number, that's not going to affect the correlation, okay? And so kind of the big thing here is that changing the units of one of the variables will not affect correlation. So if you measured something in inches, okay, so you measure someone's height in inches, you know, some person is 70 inches, some person's 60 inches, and you say, what's the correlation between someone's height in inches and their weight, maybe you get a correlation of 0.72, okay? And then if you go about and you convert all of the measurements from height into, say, from inches into centimeters, and you convert all of, or even if you leave them all as pounds, but you converted height into centimeters, and you calculate the correlation, it's not going to be affected, okay? So changing units will not affect the correlation, because changing units is basically multiplying by a constant or adding a constant, okay? So if you're changing from Celsius to Fahrenheit, you know, you're adding a constant and multiplying by a constant. It's not going to affect the correlation, okay? And then another kind of side effect of that is that slope is unrelated to correlation, okay? So you can have two plots. Let me see if I could show you okay. So here, this plot and this plot, in this case, we have a straight line, and the correlation is -1 because all the dots line up perfectly on a straight line, okay? And here is another plot, okay, where the slope is a lot more shallow, but all the dots are still also in a perfect straight line, okay? In both cases, the correlation is -1, okay? It's -1 because they're in a perfect straight line, so there's no scatter, very strong linear relationship. And it's negative because in both cases, the slope is kind of downward in that large X goes with small x over here goes with large Y, okay? Large X over here goes with small y, and small x goes with large Y, okay? You know, at least, you know, the difference between small and large Y is kind of a, you know, a smaller range here, but again, up here would be the large Y, and down here would be the small y, and that's what we have. The large X goes with the small y, the small x goes with the large Y, okay? So in both of these cases, even though the slopes are very different, the correlation is -1, okay? And that's because correlation is not related to slope, or slope is not related to correlation, okay? However, if you get this, okay, if the line ends up being flat, then the large x or small x values are associated neither with large or small values of y, because there's only one value of y. So we can't say this is a large or small value of y. So there's no correlation here. R here is 0 because the line is flat. Maybe I should probably throw this into the slides here, okay? Another thing is that correlation itself is unitless, okay? So your X values and your Y values might have units, right? You might measure height in inches or centimeters. You might measure weight in pounds or kilograms or whatever it might be, okay? And so the individual X and the individual Y values might have units, but the correlation itself is unitless. The correlation just kind of measures the strength between the X and Y variables. And again, because changing the units doesn't affect the correlation, you know, R is unitless, so you can switch from X, you can switch from, you know, centimeters to inches or something, and it's not going to affect the correlation. The correlation itself is unitless. Okay, so we have a couple questions. One says, would you be able to explain the idea of slope being unrelated to correlation using another example as well? Okay, and then another question says, will R equal 0 if there's only one value of X and you get a perfectly vertical line? And all right, so let me do another example, okay, where slope is unrelated to correlation. Okay, so if I change the units, okay, on something, that's going to change my slope. So if so let me okay. So let's say I've got some kind of plot here. All right, so I don't know, let's say we measured okay. All right, so here is, I don't know, okay, so let's say this is the relationship between height and weight. Okay, so if you think about what, oops. Okay, and let's say I draw a line here, okay? And here, maybe height is measured in inches and weight is measured in pounds. And I don't know what this is, but maybe what the slope is going to be equal to something like 5 pounds per inch. Okay, which generally means that if you compare heights, okay, so basically our slope is equal to 5. Okay, meaning that if the height goes up 1 inch, we expect the weight to go up 5 pounds. Okay, and we'll describe this later. Okay, so if height goes up 1 inch, we expect weight to increase 5 pounds. Okay, I'm making that up. I don't even know what this is. Okay, now I could take the same thing, the same plot, okay, except we're going to measure height this time in centimeters. Okay, now if you think about what happens if we measure height in centimeters, okay, effectively what happens is that maybe on the low end we have what do we have? 5 feet. 5 feet. 4 feet is 48. So let's say 410. So let's say go from 58 inches to say 6'4", so 76 inches. Okay. So if I convert that to centimeters, okay. So if I say 58 inches in centimeters, okay. So we go from around 147 to 76, 193, okay, 193 centimeters, okay. Basically, what I've done is I've just stretched out, if I put these on the same scale, basically one line would look like this, and then the other line would be kind of stretched out if they were put on the same scale, okay. So the slope is different. Basically, I've just changed the units here, and so if you're keeping track of the slope, you know, the change in y divided by the change in x, you know, this one has a much lower slope. And so here what we have is our slope might be, we have a 5 pound increase, 5 pound increase for every 2.54 centimeters. Okay, but I'm going to just round off to 2.5 centimeters. And so here my slope is going to be equal to 2. So I have a much more shallow slope, okay? If height goes up 1 centimeter, we expect weight to go up to increase, you know, around 2 pounds, a little bit less than 2 pounds. Okay, and so here our slope is less. Okay, but did kind of the relative position of the points change at all? No, the overall correlation is the correlation remains the same, right? So correlation. Okay, is that all right? I hope that clarifies. Let me know if it doesn't. Okay, and then another question that came in was, will r equal 0 if there's only one unit of x? And the answer is yes. So I had a plot here, all right? So here we would say, so this is a silly example, but we say, is there a relationship between someone's income and how many fingers they have, right? So yeah, I recognize not everybody has 10 fingers, but if you collect, you know, just a medium-sized data set, like if you survey 100 people, you know, there's a decent probability that all 100 people will have 10 fingers, okay? And so, but you know, the 100 people will have different amounts of income. Is there going to be a relationship between income and number of fingers? And the answer is going to be no. We're not going to see a relationship between income and number of fingers, okay? And if I swapped them, and I said, is there a relationship between number of fingers and income? Okay, so the correlation here, up here is 0. And here, you know, swapping variables doesn't affect the correlation. The correlation here will also be 0, okay? And so basically, if you only observe one y value for all the different x values that you have, you're going to have a correlation of 0. And if you only gathered data where x is equal to one particular value, you're not going to find any correlation, because correlation is basically if you have big X or small x, is that associated with a big Y or small y? And in this case, you only have one value of X or you have only one value of Y. And so you can't say large values of X go with large or small values of Y because there's only one value of Y. And here you can't talk about large or small values of X because there's only one value of X. So in both of these cases, the correlation is 0. And we'd say the trend is neither positive nor negative here. Okay, so I hope that answers both of your questions there. Okay, and this is also very important. The interpretation of R, as far as correlation goes, is only useful for a linear relationship. So technically, you can, it's just the result of a formula. You can throw your data points into a formula, and you'll get some kind of number, but the interpretation is not going to be meaningful. Okay? A correlation of 0 does not mean that there's no association, but just that there's no linear association, right? So if I scroll back to slide 18 here, okay, this would have a correlation of 0, but there's definitely a relationship. There is a relationship between X and Y. It's just not a straight line one, okay? So correlation of 0 doesn't mean that there's no association, just that there's no linear association, okay? So you should always graph your data first before you compute R to kind of make sure that the association is linear. Right? Okay, so we have another question. It says, we mentioned that correlation does not mean causation. So are correlation coefficients and scatter plots only used for observational studies and not controlled experiments? So you can use correlation and scatter plots for both observational studies and controlled experiments, okay? This is just another tool for describing relationships. It's just what kind of conclusions can you draw, okay? So if you have an observational study and you create a scatter plot, maybe you find a strong relationship, but you can't draw a cause and effect conclusion. However, if you set up a controlled experiment, okay, and you create a scatter plot and there's a trend, you might be able to draw a cause and effect conclusion. So you might say, is there a relationship between the dosage of my drug that I'm using and the effect that it has on the user, right? So maybe you say on this, like you have pain medication or something, right? And we say, okay, this person, we gave them, you know, this many milliliters of, say, morphine or something, and we ask them how much pain relief do you experience? And they might say, I only experience a little bit of pain relief, right? And then as you increase that dosage, and we say, how much pain relief are you experiencing? We're probably going to see a trend, right? And if it's a controlled experiment where we don't tell the user, hey, you get to pick how much drug you use, but it's in a controlled setting, and we say, all right, we're going to try out this dosage and this dosage, and this person's getting placebo, you know, with this thing, and we say, all right, and now when we look at this, we're seeing definitely a strong relationship between, you know, increased amounts of dosage with increased amounts of pain relief. Then we might be able to draw a cause and effect conclusion. Okay, the key here is you can't just look at a graph and make a cause and effect conclusion. You have to think about how the data was collected, right? So, you know, if, you know, going back to this, if there were some highly unethical experience, yeah, I don't want to talk about this, but like if some weird thing where we were able to control this in an experimental setting, you know, we might be able to draw some kind of cause and effect conclusion. I can't imagine a controlled experiment where we have this, but let's see if there is yeah, actually none of these plots could really be a controlled experiment. All of these are kind of observational. But you can have, sorry, just all of the plots I've done so far have been from observational studies, but you can do a controlled experiment where you control how much X you are using, and you measure the effect on the Y, and in that case you can draw a cause and effect conclusion, but that's mostly depends on how the data was gathered. So okay, why don't we take a 5-minute break here, and we'll come back, and we'll finish off our lecture looking at linear regression, and we'll come up with these equations here. So we'll take 5 minutes. Okay. All right. So we have a question came in. It says, do we simply observe by eye to tell if a scatter plot describes a linear relationship, or do you need to carry out calculations? Okay. So for the intro stats level class, yes, just look by eye and you say, hey, does this thing look linear? Yeah, I guess so. And that is fine, okay? Our eyes, I don't know, over the course of time, many generations, we've gotten very good at identifying patterns. Like we can look out at things and we will recognize things that look like lines. We will recognize things that look like faces. You can look at the clouds and you will see shapes and patterns and things, you know, in places where they're not really there, right? But you can look at the clouds, you can look at the stars, and we will recognize, sorry, I got my window open and trucks driving by. So, you know, we can look at these places like, you know, the stars and the clouds and recognize and find things that look like lines and things that look like shapes. And so that is fine. That's fine. Calculations do exist to see if things are linear or not, but in all honesty, the calculations don't really outperform the human brain and the human eye. Okay, so looking at things with eyes generally are best bet. Now that does mean you're going to get some situations where two people might disagree a little bit on whether something is linear or not, and you know, just the fact that a couple people might disagree on whether something is linear or not probably means this is kind of at the edge case of whether something really is linear or not. And it's probably going to be a borderline case anyway. And the calculations, if you were to do calculations, probably reflect the same thing. So that's just what we do. So just plot it, just graph it, and decide, if it looks like a straight line or not. All right, so let's talk about linear regression. Linear regression is going to be kind of the tool that we use. So we've talked about correlation to quantify the strength and direction of a relationship. And what linear regression is going to do now is it's going to create basically the equation of a line for that trend line. So when you have a scatter plot and you draw a trend line, you might want to give that trend line an actual linear equation, something with a slope and an intercept. And that's what we're going to do with linear regression, okay? So the linear regression line is a way for us to describe the relationship with an equation, okay? It's useful for making predictions and for understanding the relationship, all right? So when we talk about the equation of a line, probably in algebra you learned like y equals mx plus b. Here in our stats class we use y hat equals a plus bx, okay? Y hat represents the predicted value of y. To kind of distinguish between the actual values y and the predicted values y, we put a little hat, this little cap here over the y to indicate that this is a predicted value and not the actual value of y. Okay, so the y hat is the predicted value. And then we still have a slope. Slope is b and the intercept is a. Okay, so it's still slope and intercept for the linear equation, and this is what we have. And we're gonna learn how to make this thing. Okay, depending on the textbook, you often have different names for x and y. And so it's possible that you, in one of your other classes, you heard one of these other names, such as the independent variable or predictor variable or something like that. And so these are names that we often hear for the x variable. We have the explanatory variable, the predictor variable, the input variable, or the independent variable, okay? And then other names that we can use for the y variable are things like the response variable, the predicted variable, and the outcome variable, and the dependent variable, okay? Probably my least favorite of these are independent and dependent variable. Later on, when we cover probability, we will have formal definitions for what independent and dependent events are, and also, and they don't quite align with the usage of independent and dependent variable here. An independent and dependent variable for x and y imply a little bit of a cause and effect relationship. There's kind of a, that x is independent yet y is dependent on x, and that implies cause and effect. And when we're talking about correlation, I really want you to be cautious about jumping to cause and effect conclusions. Actually, I would say strongly, don't jump to a cause and effect conclusion. Correlation, just because there is a correlation, there might be a cause and effect relationship, but there might not be. We have to be careful about that. Okay, so here is an example of a regression equation that could be created, right? So it looks like we're looking at used car information, and yeah, I think this is made up data, but we can pretend it's real, okay? And we're looking at the relationship between the age of a car and its value in dollars. And the regression equation is this. We predict the value of the car to be 21,375 minus 1215 times age, okay? Which basically means each year that goes by, we predict the value of the car to go down, okay? So each year that goes by, we're predicting the value of the car to go down about $1,200, so that you know, when the car is around 10 years, when the car is new, we predict it to be worth around $21,000. When the car is around 10 years old, we expect its value to be around $10,000. I think that's quite generous for the depreciation of a car, but here's just some made-up regression equation that, you know, it could work, and that as the years go by, we expect the value of the car to go down. Okay, and this is what it looks like. This is our intercept, and here's our slope. In our case, the x variable is the age of car measured in years, and the predicted value, I'm assuming, is US dollars. Okay, so we have predicted value is 21,375 minus 1215 times age. So if we were to predict the value of a car that's 12 years old, we would plug in 12 for the age, okay? And our predicted value would be 21,375 minus 1215 times 12. 1215 times 12 is 14,580, and we predict the value to be around $6,800, $6,795. So our prediction for the 12-year-old car is that its value is $6,795. This is just a prediction. The actual value of a car that's 12 years old could be higher or lower than this, okay? All right, so here is a simple data set, okay? And here we're gonna try to predict height based on weight, okay? So this time our x variable is gonna be weight, and based on someone's weight, we're gonna try to predict the person's height, okay? And this is probably not, you know, who knows? And we only have 6 data points, but here, this is the plot of the 6 data points. And what we're gonna do is we're gonna fit the trend line, okay? And so if you want to create the regression equation in R, the function you can use is LM. LM stands for linear model, and that we want to find a linear regression equation, okay? And when we write the relationship, we're going to write height tilde weight, okay? And this is the shorthand way of R saying predict the variable height based on the variable weight, okay? And so we would write linear model LM, height tilde weight. This is predict height based on the variable weight. And data comes from the data frame dat, okay? And we created the data frame dat back here. So here's our data frame dat, which has the columns weight and height, and we are creating this, okay? And we are going to store the results of linear model into just an object that I've arbitrarily decided to call model. Now, this name could be anything that you want it to be, but here we've called it model. And when we ask, okay, well, what is the result? What is model? It comes back and it tells me that the coefficient, the intercept, is 52.39726, and the slope associated with weight is 0.08595, okay? So the intercept is this value, that's 52.397, and the slope is 0.08595. And so when we put them together, then this is going to be our predicted height is equal to the intercept plus the slope times our x variable weight, okay? So we're getting our output, our y variable that we're predicting is equal to the intercept plus the slope times the weight. Okay. And you can plot this, right? So you can create the plot. Here's the plot of the data points, and then you can draw the fit line by calling AB line on the model that we had created. And so when you do this, R plots the fitted line, and this red line represents the fitted line that we have here. Okay, and so it can be done very quickly in R using this function LM. Okay, we can also find the regression equation ourselves using summary statistics. Okay, so it can be done. And you would need these 5 summary statistics. You would need the mean of the x values, so that's x bar, and you'd also need the standard deviation of the x values, which is given by s sub x, okay? You'll need the mean of the y values, y bar, and the standard deviation of the y values, s sub y, and the correlation between x and y, which is the value r. Okay, so if you have these things, these can be combined to create our, to find the slope and intercept, okay? So here I've gone ahead and I found all of these things, x bar, s standard deviation of x, y bar standard deviation of y, and the correlation here, okay? Is the regression equation the same as the equation of the line of best fit? Yes, yes. The regression equation is the same as the line of best fit line, okay? All right, so basically what I've done is, here I've got these values and I said, well, what is the mean of these 6 values? If I do 104 plus 110 plus 141 plus 125 plus 170 plus 160, and I take the mean, we would get 135. If I go back and I say, what's the standard deviation of these 6 numbers? We can ask the computer to do that, and that's what we get. Okay, so that's what I have here. Okay, and the correlation between the 2 variables is 0.88. Okay, question, is it common to find the regression equation by hand? Common, maybe not super common, but it's enough. I think I think it's reasonable to include it in the homework and possibly a quiz or exam question as well. So, you know, frequently you would ask the computer to calculate, do some of these calculations for you, okay? Especially correlation, just because correlation can get really tedious. The calculations here are not as tedious, okay? It's a little bit, I think, more reasonable. And so, I kind of want to demonstrate that, and I think it's reasonable to ask a question here. Okay, can I go back to the slide on how to find it from summary statistics for a second? Okay, I actually haven't given you the formula yet, okay? I just said you need to find these 5 summary statistics, the mean of the x, the mean of the y, standard deviation of x and standard deviation of y, and the correlation of x and y, okay? So these are the values you need to do. And we have learned how to calculate these things, right? So the mean of x, you guys know how to find the mean of a column of values. And then the standard deviation, we learned that last week. And then the correlation, I did not teach you, but I said we just use a calculator or computer to calculate the correlation. But the mean and the standard deviation, you know how to calculate. It's just that you have to do it twice, because you have a column of x values and you have a column of y values. So you have to find the mean of the x column, you have to find the mean of the y column, you have to find the standard deviation of the x column, standard deviation of the y column. So you have to do these things, and you can find the correlation. So I've just gone ahead and done these using the calculator, the computer, to find the mean and standard deviation of these variables, okay? And then the correlation can also be found using core, okay? What is the syntax to see out the slope and intercept of a linear regression using R? Okay, so so you can create the linear regression equation here, LM, and create a model. And then when you ask what is the result of the model, it will spit out kind of the calculation of the intercept and the calculation of the slope. And I just want to show you that these numbers you can find yourself, and not just, you don't have to use LM to do this, okay? All right, so we have the mean and standard deviation for all of these things, okay? And so this is how we would calculate the slope. The slope is the correlation times the standard deviation of y divided by the standard deviation of x. Okay, so the correlation between x and y is 0.8809. And then the standard deviation of y is 2.607. and the standard deviation of x is 26.728, all right? So if I put in 2.607 and 26.728, I plug in those numbers, and I do the calculation, I get 0.08595, okay? And indeed, if I go back here, the slope for our linear regression line is 0.08595, okay? How do we get this intercept of 52.397? The intercept is found by taking y bar minus b times x bar, okay? So you have to find the slope first, which is your b, okay? So you take the y bar, which is the mean of y, 64 inches, subtract off b, which is this slope, 0.08595, times the mean of x bar, 135, and when you do that, you get an intercept of 52.397, okay? And so this is how you can get the slope and the intercept yourself if you were asked to find these values by hand. And it's also to show that it's not just some mystery where the computer just, you plug in numbers and the computer just spits something out by magic, okay? It's not magic. You can get these numbers yourself, okay? And it's found using these equations here. All right. So the regression equation that we've established, okay, either by finding it ourselves or using the computer to find it, is that the predicted height is 52.397 plus 0.08595 times the weight, okay? And if we want to make a prediction, you just plug in whatever value you have for the weight. So if a person has a weight of 170 pounds, we plug in this value, okay? And then, and it gets calculated, and the height is 67.0085. Okay, so the predicted height will be 67.0085. Okay, and in our data, we can look, right, at our data, and there is somebody, okay, who weighs 170 pounds, and their height is 66, okay? So the person who weighs 170 pounds, their height is 66. According to this regression line, we predict their height to be around 67. So this is the actual value. This is what the red line represents where this person, what we predict this person's height to be. Okay. And so, so this is what we have, okay? So this person weighs 170. We predict, the line in red predicts a height of 67, and this person's actual height is 66. The residual is the difference between the actual value and the predicted value, okay? So the residual takes the actual value of 66 inches, and we subtract off our predicted value of 67.0085, and the residual is going to be negative 1.0085, negative 1.005. Okay, there's a question. Is there a group me for this class? I don't know. I don't know if anybody has created a group me for the class. I did set up the campus wire, and I hope you guys join. I think it's a good place to do that. Oh yeah, I forgot to give you the quiz answers. Yes, second quiz answer for today. Thank you for that reminder. Second quiz answer for week 2 Monday is C. C as in cat. C as in cat. I don't know, Charlie. What starts with a C, right? Yeah, C as in cat. So that's our second quiz answer for today. Yeah, so I've given just the first two, and I'll make sure, or if I don't, remind me to give you the third quiz answer. So second quiz answer today is C as in cat. Okay, so the residual is the difference between the actual value and the predicted value. Okay, and so here our residual for that data point is -1 because we predicted 67 and the actual value is 66. All right. And so, you know, when we create a linear regression line, what's going to happen is that the line will always pass through the point x bar, y bar, okay? So that means if the observation has an average value of x, we predict it's going to have an average value of y, okay? Average value of x is associated with an average value of y. The linear regression line is also going to minimize the sum of squared residuals, okay? And so I want to kind of illustrate what we mean, all right? So I don't know if you've heard of this. So the linear regression line is sometimes called the least squares line. All right, let me zoom in here, okay? And so here we have these different dots, okay? And the red line here represents the kind of the fitted line, the prediction line, okay? And the vertical distance from each dot to this red line represents the residual, okay? So sometimes the dot is above the red line and you have a positive residual, okay? That's the vertical side, vertical line. And then a vertical line going from this dot, which is below the residual prediction line, is a residual. And on this thing, what I can do is I can adjust what the intercept is, okay? So adjusting the intercept will slide the line up and down, okay? And so what we can see is that I can put this line right here, okay? And it runs straight through this purple dot. This purple dot has no residual, but it has a fairly big residual for this brown dot here, okay? So the brown dot has a big residual, and when you square that residual, you get a big brown square, okay? I can move the line further. I can move it down so that the line goes through the brown dot, okay? If I do that, the brown dot has no residual. There's no brown square here, but you can see that there is going to be a big residual for the orange and the green dots, okay? The orange and the green dots have big residuals. There is a big difference between what the line predicts and what the actual value is, okay? And so this residual, when you square it, forms a very big squared residual represented by this big green square and this big orange square, okay? And so what we're aiming for is we're looking for a line that kind of minimizes the total size of all of these squared residuals. So if we scroll up or down, we're looking for something that minimizes the total squared residuals. And you can also adjust the slope, okay? And we're looking for a combination so that the resulting fitted line will end up with kind of the total squares that's as small as possible, right? So we can say this is no good because the squares of the residuals ends up being a huge value, okay? Whereas something around here seems pretty good, and we're trying to, you know, adjust the slope so that the total size of the squares is as small as possible. That's the goal, is to get the total squares as small as possible. And so that's what we mean by the line will minimize the sum of the squared residuals. The squared residuals, the residual is the distance, the vertical distance from each dot to the line. And when you square that, you form a literal square, okay, right? You take one on the side and you make a square out of it, and that's going to give you this area, the squared residual, and that's what the linear regression line. The linear regression line will minimize the sum of the squared residuals. There's no other straight line that you can have that's going to produce a smaller total squared residual. Okay, so when we create a regression line, it can be useful for understanding the relationship, okay, between variables here, right? And so the slope, this is the interpretation for the slope, okay? It tells us how much our prediction for y changes when the x variable goes up by 1 unit. Okay, so in our case, with weight and height, the slope is around 0.086, okay? Y is height in inches and x is weight in pounds. And so this means that when weight, the x variable, goes up 1 pound, our prediction for height goes up 0.086 inches, okay? So when we say the x, so that's what we're saying, okay? It's how much our prediction for y changes when the x variable goes up by 1. So if x goes up 1 pound, our prediction for the height goes up 0.086 inches, okay? Now, when we say the x variable goes up by 1, we're not forcing x to increase by 1, okay? We're not saying that if somebody gains weight, they're going to get taller, okay? That's not how it works. We're not saying that one is causing the other, and you can't say that we're changing it. We're just saying that if there's two people, all right? So if there's one person who weighs 100 pounds, we might predict their height is 61 inches, okay? And if there's another person who weighs 101 pounds, we would predict that person's height to be 61.086 inches, okay? The difference between their predictions is 0.086, okay? So we're just saying if you're comparing one person to another person, and the difference between this person and this person is 1 unit of x, in this case 1 pound, 100 pounds to 101 pounds, our difference in predictions for their height will be different by the amount of the slope, 0.086 inches, okay? We're not saying we can force an increase of x onto this person. We can't say this person, we're gonna make them eat more, they're gonna gain weight, and when they gain weight, they're gonna get taller. That's not what we're saying, okay? That doesn't make sense, okay? We're just saying if we're comparing two people, there's a difference of 1 unit between this person and this person. Our prediction for their height, their y variable, is going to be different by whatever size the slope is, okay? So if the difference in weight is 10 pounds, okay, if we have one person that weighs 100 pounds and another person that weighs 110 pounds, you know, their difference in height we predict would be 10 times the slope, so 0.86, right? It would have 61 and 61.86, almost 62. So if we look at the cars, okay, you know, the value is measured in dollars and the age is measured in years. So if the age of the car goes up by 1 year, our prediction goes down $1,215, okay? So we would predict a 5-year-old car to have a value of 15,300. If we want to predict the value of a 6-year-old car, we could just subtract 1215 from this and we would predict its value to be something around 14,085. Okay. So that's what we have for interpreting the slope. Okay. As far as the intercept goes, the intercept is our predicted value if x is equal to 0. Okay. The intercept is only meaningful if it makes sense for x to equal 0. So when we're talking about predicting the value of the car, sure, can you have a car with an age 0? Yeah, you can, okay? Age 0 means you have a new car, and we would predict the value to be the value of the intercept, $21,375. So this is what we're predicting to be the value of a new car, okay? In this case, when here we're predicting someone's height based on their weight, okay? You cannot have a person with a weight of 0, okay? It doesn't make sense for x to equal 0, so there's not a meaningful interpretation for the intercept, okay? The intercept here is not going to be useful because you cannot plug in 0 for a weight, okay? A weight of 0 is like no person, right? That's not going to work. So in some cases, the intercept doesn't have a useful interpretation, okay? All right, so we're gonna wrap up today's lesson with a whole bunch of warnings, okay? In that, you know, linear regression is a very useful tool, okay? Correlation, linear regression, very useful. Statisticians love to use it, okay? But it's also misused, okay? In that people don't often heed these warnings, will create linear regression equations in situations where they shouldn't, you know, will do things with it that they should not, okay? So number one, don't use a linear model to describe a non-linear relationship, right? So if you have something that looks like a U, or if it curves up, if it looks like it's taking off like an exponential, if it's going and it's becoming steady or something like that, a linear equation where you're predicting a straight line is not going to do a good job, okay? So you should always look at a scatter plot, okay? Always look at a scatter plot to say, hey, does this look like a straight line? And you go off of that, okay? You also have to be careful about outliers. Outliers can have a big effect on the resulting correlation. And so you should always create a scatter plot just to see, hey, are there any outliers, right? And it's hard to notice outliers just from looking at a table of data. But when you create a scatter plot, it's a lot easier to identify outliers. Our eyes, our visual processing is much better at being able to pick out outliers. So always keep that in mind, right? So here's just kind of this is a toy example data set known as Anscombe's quartet. Okay, so so Anscombe was a statistician, and he came up with these 4 examples, all right? And so here's an interesting thing. All 4 of these plots, if you take these points and you plug them into the correlation equation, they're going to spit out the same correlation value. All 4 plots have the same correlation R. All 4 plots also, if you look at these regression lines, the blue line of best fit, all 4 plots have the same line of best fit, okay? Now, if you did not create the scatter plot and you're looking only at the summary values, okay, all of the summary values would end up actually looking the same. All 4 plots have the same X bar, all 4 plots have the same Y bar, all 4 plots have the same standard deviation of X, standard deviation of Y, all 4 of them have the same correlation between X and Y, and all 4 have the same regression line. And so if you look only at the summary values without looking at the plot itself, you might think they're all the same, but they're not, okay? It makes sense to use linear regression for this first example. There's some scatter and there's a linear trend, and it makes sense to use this, okay? Here, this is clearly not a linear relationship, okay? Not a linear relationship, and yet we get the same correlation and the same regression line, okay? What we need to do is we need to use some kind of curved line to describe the relationship. And to use a straight line is not a good idea, okay? Over here, it seems to be quite clear that these dots are in a straight line, and we have one outlier that's throwing everything off, okay? And so probably the line of best fit should just run through these dots, and this one dot might be a mistake. Maybe it was a typo whenever they entered it, okay? We should probably remove this and redo it and fit a line that fits the other points quite clearly. But again, just because of this one outlier, it's throwing off the regression line, it's throwing off our correlation quite a bit, okay? And over here, this is what's going on, is we've basically gathered data where X is one value. We've gathered a whole bunch of data points where X has is the number 8 for everybody, okay? And then we have one observation where X is like 19, okay? And when X is 19, suddenly we're forming an entire trend between X and Y based on this one observation at 19, okay? And that would be, you know, it would be kind of like we're asking, is there a relationship between the number of fingers and someone's income? And then you survey, you know, 50 people, how many fingers do you have and how much money do you make? And you get, you know, a whole bunch of different numbers. And so far you have no relationship between the number of fingers and income. And then let's say somewhere along the way you encounter someone who has, I don't know, maybe they lost a finger somewhere along in their life. So they have 9 fingers, okay? So that this person has 9 fingers, and yet this person was also very successful. Maybe their income is like $1 million, okay? And if you do that, suddenly you'll find a trend that appears to there to be a relationship between number of fingers and income. And it might even suggest that, you know, the relationship might be negative and that the person with fewer fingers has a much higher income. And then if you draw a cause and effect conclusion, you might be tempted to think, well, I should get rid of some fingers because that's going to increase my income. Obviously, that's silly, but that's basically what's going on here. We've taken a whole bunch of observations where X is the same value. We have one observation where X is different, and then we're basing an entire trend on that one observation where X is different. So don't do that, okay? Basically, this page summarizes what I've talked about with these 4 different plots here. Okay. A few more warnings that I think you guys are aware of. Correlation is not causation. We've talked about this already. Just because you see an association doesn't mean that there's a cause and effect conclusion. There could be a cause and effect conclusion. And generally, if there is a cause and effect conclusion, there's generally going to be correlation, but you can't go the other way around. If there's correlation, you can't jump to a cause and effect conclusion. Okay. And then there's the idea of extrapolation. Don't make predictions beyond the range of the data where you've collected, because you can't be sure that the linear trend will continue beyond the range of data. So a silly example is, let's say there's a child and you measure your child's height from age 3 through age 10, okay? Every month you measure the child's height, and every month the child gets a little bit taller. And you see this linear trend between age and height between ages 3 through 10, okay? Maybe even 3 through 13, okay? So for the past 10 years, we've seen this linear trend. And you might be tempted to extrapolate and say, okay, well, this will continue on for the next 10, 20 years. And then you'll say, well, by the time my child is, 33, 43, he's gonna be, 15 feet tall, okay? Obviously, we know that's not how human height works. Kids grow until they're around, I don't know, 15 to 20 years old, somewhere in there. People stop growing, and then their height remains fairly constant throughout their adulthood, and then maybe changing in their later years of life. And we know this, so we know that's a silly example, but there are many times where people will say, hey, this trend has held up for the past 10 years, 20 years, maybe even the past 100 years. And they say, well, therefore, this is what the world's going to look like 100 years into the future. We have no idea what the world's going to look like 100 years into the future. Things can take off, get exponentially worse. They might stabilize. Who knows? Okay. There's one last definition. R squared is the coefficient of determination. You can take your correlation value and you square it and you get something R squared. Correlation is always between -1 and +1, so R squared is always going to be between 0 and 1. And basically, this often shows up in a summary table. A larger R squared value means a stronger relationship. Okay, and I don't want to get into the technicalities of this definition, but it measures how much variation in the response variable and the Y variable that is explained by the X variable or explanatory variable. Okay, let me give you your last quiz answer today, and I apologize for going a few minutes over. Last quiz answer is A as in apple. A as in apple is your third quiz answer. You should be able to take that viewing quiz. So third quiz answer is A as in apple, and that's it for today. So we will see you guys on Wednesday. Thanks for joining us, and have a good day.